Okay, now we're going to look at some typical NMR splitting patterns in the aromatic region. And we already looked at one of those, and that was what happens if you have a para-substituted species where both groups are the same. You'll end up with just a singlet in that region, no splitting at all. Probably simplest pattern we'll come across. Let's take a look at another one. Okay, there's a lot of stuff going on in here. Again, aromatic region, around 6.5 to 8. But notice most of these peaks are closer to 8 than to 7. There's something electron withdrawing or electronegative that's causing some de-shielding here. And if we zoom in, we've got a doublet, a triplet, and a doublet. This is actually an idealized splitting pattern for something that is mono-substituted. And for something mono-substituted, so we only have one thing attached to our ring. And I'm going to map this out. We have a couple of ortho hydrogens here, ortho to that carbonyl, then a couple of meta hydrogens, and one para hydrogen. And ortho hydrogen, he has one neighbor, and we expect him to be a doublet, and that's what we have right here. The meta hydrogen, he has two neighbors. So if you have two neighbors, number of neighbors plus 1 tells you you're splitting. We expect him to be a triplet, and he is actually right here. We look at the para, he has two neighbors, again a triplet, right here. Notice I have two triplets though. How do I know which is which? Here's the way you do that. There are two meta hydrogens, so you're going to have a taller signal. You only have one para hydrogen, so your smaller signal is this guy. And there's also another way to tell who is who, and that's to use our old friend resonance. You can actually put a full positive charge at the ortho or para positions in this compound. And a partial positive means you're de-shielding your signal. If you're de-shielding, de-shielded signals appear to the left. So the ortho and para are the most downfield signals. The only place where we cannot put a positive charge in any of these resonance structures is on the meta position. He's our most upfield signal in the aromatic region. So that resonance will actually tell you which hydrogen belongs to which signal. Very handy. Now if we happen to have a group on there that shoved electron density into the ring, that would actually reverse the order of these signals. And you'll see the triplet out here, little triplet and a doublet. So you can sometimes tell right away whether you have something that donates electron density or withdraws it. Let's take a look at another one. So this guy, a little bit more complex here. We just see kind of a blob here. Even when you zoom in, you're going to see that. But I want to call attention to the integration pattern here. And this compound is actually C8H10, an isomer of the one we looked at before. I'm going to draw in the bottom of those integration lines. I'm going to highlight. There's a top of an integration line. That's where a little integration line bends. And here's the top of an integration line, kind of hard to see. But I'm just going to put in a couple lines. So I measure the distance here. Remember, we go by the integration line, not the height of the signal. Very important. And let's compare it to what's happening over here. Notice this spacing and this spacing are different. It's not a 1:2 ratio between those two signals on the right. It's actually a 2:3 ratio. Which we've seen before last semester. Now if we jump back over here, let's not forget we got an integration line up top. Let's put in a signal there, and this is a pretty wide gap. We're going to put in another hash mark for our hydrogen ruler. And we've got 1, 2, 3, 4, 5 hydrogens in this signal. Here's our ratio, 5 to 2 to 3. And we also know that this is the aromatic region. So we have to have a benzene ring. That takes care of 6 of our carbons right off the bat. And there are 5 hydrogens on that benzene ring. That means this has to be monosubstituted. We don't have a choice here. Now we jump over here. We've got a 2:3 ratio. If you look back in your notes from 235 lab, when you have a 2:3 ratio, when you have a quartet and a triplet, that is the signature for an ethyl group. This is a 2-piece puzzle. This has to be ethylbenzene. And that illustrates one thing about these groups. You don't always see the idealized splitting pattern. This guy is not a very strong electron donator. And so while we can see a triplet here, we don't see the doublet or the small triplet. They kind of merge together. Although it doesn't matter because we know that this guy is mono-substituted because of the integration pattern. Let's take a look at another common pattern. And let's see, this fellow would be C7, H7, BRO. And we can even zoom in a little bit. And so we actually have a doublet in this region and a doublet over here. 2 symmetrical doublets about the same size. It's kind of important. And let's see, there's the top of your integration line. There's the top of that integration line. And if you draw a little line across here, here's the bottom of the integration line. We actually have a 2:2:3 ratio here. 2 plus 2 plus 3 adds up to 7. That means we have 2 types of hydrogen in this environment, 2 types in this environment, 3 over here. And so we can start doing a little bit of puzzle piece making here. So this guy has to be a CH3 group. That's a good choice there. So CH3. And we have a benzene ring. That takes care of 6 of your hydrogens, or 6 of your carbons, and in this case 4 of the hydrogens. So C6H4. And that just leaves a bromine and an oxygen. So let's put a bromine on here. Bromine just bonds like that. Oxygen, he can bond like that. And we definitely have a benzene ring in here. And that benzene ring, since it only has 4 hydrogens, has to have 2 substituents on it. And in order to get 2 symmetrical doublets, that's the dead giveaway of a para-substituted benzene ring. Here's our puzzle pieces: a benzene, a methyl, a bromine, and an oxygen. Now it's pretty rare that you'll stick a bromine on an oxygen. Those 2 electronegative atoms, they're going to fight over that bond. It'll probably fall apart. But I'm going to use a clue from where the signal shows up, the chemical shift. If you happen to have a signal at 4, that's a dead giveaway of a hydrogen that's attached to a carbon that's next to an oxygen. You find that in esters, alcohols, and ethers. So if I make my puzzle piece like this, an OCH3 group, I've solved my puzzle. There's only one way to put that together, because I have a bromine on one side, the methoxy group on the other, in a para relationship. And so that's what we have here. I need to correct this in that HB and HC are actually different. So we actually have 3 signals here. And so B and C will split each other, and so you'll get 2 doublets, 2 hydrogen doublets. And this guy will just be a singlet over here. So again, you draw those puzzle pieces and bring the puzzle together. You do that for any of these. In fact, think of NMR as being a logic puzzle, kind of like a Sudoku puzzle or something like that. So if you like logic puzzles, NMR is for you. And I'm waiting any day now for the local newspaper to put an NMR puzzle right next door to their crossword or Sudoku. I may be waiting a long time for that.